Today, I'm going to answer what might be one of the hardest to answer questions in all of FPV. And it's hard to answer because it's so open-ended. If I'm starting from scratch and I want to pick a drone or design a drone, how do I know what size prop, what size motor, what kV of motor, what battery voltage, what size of battery do I pick? And this is a very hard to answer question because it's so open-ended and there's a lot of engineering involved. And usually I just say, well, I don't know. Find somebody else who's doing approximately what you want to do and then just crib their work. Use whatever drone they use. But that doesn't always work. And wouldn't it be nice if you could have the actual theoretical background to understand how those choices are made, or to answer it for yourself in a case where maybe nobody else has done the kind of thing that you're trying to do? I'm Joshua Bardwell, and you are going to learn something today. This is a good one. I think this is going to be a controversial video. This is a very difficult question to solve without a lot of just engineering iteration. You build a drone, you try to do the thing, the drone is bad at doing the thing, and so you change something else to try to make it better at doing the thing. But engineering iteration takes time and costs money, and the idea here is that I want to get you in the ballpark of a correct answer so that when you do the inevitable engineering iteration, you're at least closer to the answer and you can get the ideal answer with less work, right? But I want to acknowledge straight up here at the beginning that the premise of this video is that you have nothing and you're starting from scratch and you want to start to design a solution that gets you in the ballpark of a correct answer. For every piece of advice that I give you in this video, you will be able to find a real-world drone that breaks that advice and still works fine, and that doesn't discount the things that I'm saying. But I do want to say at the beginning, if you're trying to solve a problem that's already been solved, if I need to carry a GoPro and I want to do freestyle tricks, or if I want to race a drone that goes fast, accelerates, and is very lightweight, those problems are already solved. The best thing you could possibly do is go look at other people who've solved those problems and learn from what they've done. Although the stuff in this video could help you understand how they got there, and so I think it's still valuable even if you're not doing something completely novel. So where do we start? And the first place we have to start is with our primary design constraint, okay? Are we designing for top speed? Am I trying to design a drone that's going to break a world speed record like Luke Bell did? No, that's not where we're coming from. Am I designing for flight time? Do I need to stay in the air for a certain amount of time? Am I designing for packable size? Do I need a drone that at minimum has a wheelbase of XYZ? Am I designing for weight? Do I need a drone to be of a certain weight? And we could pick any of those, but I think that the most universally applicable design constraint will be the payload weight. I want to carry a payload of a certain size. That could be a GoPro, it could be a cinema camera, it could be some kind of a sensor package, it could be anything that the drone is carrying. And I'm going to say, I want to put this thing in the air and I want to fly it for a certain amount of time. I want to have a reasonable amount of maneuverability, etc., etc. That's where we're going to start designing our power system. I do want to say before we move on that the payload that you're carrying could be nothing. Like if I have a 5-inch freestyle drone with a battery and no GoPro, then the GoPro would be the quote-unquote payload and the battery and the drone would be the other parts of the components, and we just set the payload weight to 0 and we proceed with the process. The process will still work even if you're not carrying a quote-unquote payload. We're going to start this process with the concept of disk loading. And disk loading is the total weight of the multirotor divided by the disk area of its propellers. So we take the size of the propeller, we calculate the area of that circle, we add up the number of propellers, and that is the disk area of the multirotor. We then divide that by the total weight of the multirotor, and that is our disk loading. I do want to acknowledge that in other domains, like a helicopter has a concept called disk loading, and that is a real-time concept that is the actual thrust, actual weight that's being applied to the helicopter. So like if the helicopter goes into a negative G dive, at the bottom of that dive, the disk loading increases, and then at the top, if it goes into a 0 G parabola, then it would have 0 disk loading at the top. That's not what we're talking about. This is a kind of a borrowed concept that's been sort of mutated a little bit. Disk loading in this case is just the weight of the multirotor divided by the disk area of its propellers. And we're going to use units of grams per square inch per square inch. Yes, square inch, not cubic inch. Grams per square inch. If you hear people talking about disk loading in other contexts, sometimes they will use grams per meter or kilograms per meter. And so the disk loading numbers that I'm going to, if somebody else is talking about disk loading, you need to make sure they're using the same units. Otherwise, the numbers won't be comparable, although it's fairly easy to convert from like grams per square meter to grams per square inch. It's just like a division or multiplication. And the formula for disk loading is up here at the top of the screen. And throughout this presentation, I will be giving you the formulas for all of the math that I'm going to show you, but you don't have to do math by hand. Oh no. Because I have a spreadsheet that I've created that goes through everything, all the math that we're going to discuss in this video, and it does all the math for you. And I'm going to tell you how you can get access to that spreadsheet not too much later in the video, but not just yet. A little YouTube teaser for you. So, for example, if we have a quadcopter with 4 props with an all-up weight of 4 kilograms running on 7.5-inch props, we end up with a disk loading, we crunch the math, and get a disk loading of 22.5. Now, what's the point of disk loading? Disk loading is a rough way of approximating the thrust to weight ratio of the quadcopter. Like a quadcopter with a heavier disk loading is going to have a lower thrust to weight ratio. A quadcopter with a lighter disk loading is going to have a higher thrust to weight ratio. We can also roughly draw an analogy between the disk loading and the RPM and speed of the props and the size of the battery, right? Those things will all play in, and there is a lot of hand waving and generalization here, but again, we're starting from nothing and we have to just find a way to kind of put some constraints on our design, and the short version is that disk loading is a good way to do that. Why don't we use thrust to weight ratio? It would be better to use thrust to weight ratio, but we don't know what prop or motor we're going to pick yet, so we don't know what the thrust of the quadcopter is. We don't know what the weight of the quadcopter is. So we're going to start with the concept of disk loading as a way of kind of getting our foot in that door. So what is a good disk loading? And the answer is it depends on what you're shooting for. If you are designing for a light, agile aircraft, not carrying much payload, like a typical freestyle drone, then you might shoot for a disk loading of about 8 to 12. If you're trying to do an aircraft that is trying to maximize flight time, and by maximize flight time, what I mean is we're going to pick the biggest battery that we can pick without excessively overloading the aircraft, because bigger battery equals more flight time. We should target a disk loading of about 18. 18 is heavy, but still maneuverable. If your disk loading is below 18, you could probably afford to go to a larger battery and extend your flight time if that was something you wanted to do, or you could go to a smaller prop and reduce your wheelbase if that was something that you wanted to do. You're not obligated to get your disk loading up to 18, and an aircraft with a lower disk loading will be more maneuverable, but it will have shorter flight time. 18 is roughly the threshold where we say you're starting to compromise flight performance in a meaningful way. A disk loading above about 25 is probably going to be high on the throttle, difficult to maneuver, and might be overworking the motors. And again, if you look at real world examples, for example, some 3-inch Cinewhoops have disk loadings closer to 30, and they still fly okay, but we're trying to generalize over a wide variety of prop sizes and motors and weights, and so we draw the line at about 25. It's not a hard line, but in general, as I'm starting a design, I wouldn't start with a target above 25. Disk loading can also be too low. If the disk loading is very low, it means that the drone is very light for the prop size that it has, and that can be fine, but generally this type of drone will either have short flight times, as in like a light, powerful racing drone, has a relatively small battery because it only needs to fly for 3 minutes at a time, and it just wants to suck all the juice out of that battery and get back and crash land with an empty battery. Or it could be like an ultralight drone, like a 4-inch long-range drone with a small battery, but because it's so light, it can still fly for 20 minutes. The thing with low disk loading is, number one, if you're designing for flight time, then you want more battery, right? You want to get that disk loading up and add more battery and more flight time. The other thing is if the disk loading is too small, then the motors and or battery are likely too small as well. And the reason for that is that the motors add weight, and so a big chunk of where the weight of the drone comes from is the motors and the battery. And so if you end up with a disk loading, and the threshold we use here is 6, if you end up with a disk loading under 6, then it's likely your battery and or your motors could be bigger. But maybe you're okay with that. Maybe you want a light disk loading, those flight characteristics may be what you're after. So now we have a target disk loading in mind. For the type of drone we're going to design, I want a disk loading of 12, 18, 22, 25. I've got a number in mind, and now I need to calculate the actual disk loading that my drone is going to have. I'm going to need an all-up weight, and I'm going to need a prop diameter in order to do that. And where am I going to get those numbers? Well, I don't know my all-up weight. All I know is my payload weight. So what I did is I looked at a whole bunch of real-world drones, from 5-inch freestyle drones carrying GoPros to 13-inch cinema drones carrying cinema cameras to a whole bunch of real-world drones that carry payloads of various sizes. And I just tried to see if there was like a ballpark trend. And what I came up with is that if you take 60% of the payload weight, that is roughly what the battery ends up weighing. And 60% of the payload weight is roughly what the rest of the drone ends up weighing. And this is the first place in this video where I expect people will go, this is bullshit, Bardwell just making this. We got to start from somewhere. Remember, we're starting from nowhere, and we're trying to just kind of bring in the boundaries on our engineering constraints. And I think this is a reasonable place to start. If you could do better, if you have an idea for what size prop and what size frame and what the payload, the actual weight of a battery and payload for a typical drone that might do what you're trying to do is, absolutely you should substitute these numbers. But if you don't have any of that stuff and you're coming from nowhere, I think that this is a reasonable assumption. And as I said before, you do not have to do that math by hand. You can just type it here into the spreadsheet, and the spreadsheet will do that math before you, calculating the battery weight, aircraft weight, and the total all-up weight. If you have actual hard numbers that you want to use, you can just type those in. I recommend that you make a copy of the spreadsheet before you do that, because like if I overwrite this cell, it'll erase the formula. So you always do your work on a spare sort of scratch paper copy. But in order to enter these numbers in the spreadsheet, you would have to have a copy of the spreadsheet. And this is the part where I tell you how you can get a copy of the spreadsheet. And not just the spreadsheet, but I also have a fully written paper which goes deep into a lot of the stuff I'm talking about here. If you'd rather read a paper than listen to a video, everything I'm going to talk about in here is in this paper. In fact, there are some things in this paper that I'm not going to talk about in this video, like I'm going to tell you how to select the prop size and all the math and so forth. Whoops. There we go. But I'm not going to go in this video into a lot of this background information, background on prop size as it relates to maximum speed, battery voltage, background, how motors work. There is a ton of secondary information in this document. Background on motor stator volume, stator shape, the myth that wider motors make more torque, and so on and so on. This spreadsheet and the associated report can be had for the low, low price of $20 if you want to get them. If not, you can take everything you want from this video, and all the information is there. But if you want those files, there's a link in the video description where you can buy them. It does go to my Patreon, but you don't have to sign up as a patron. Of course, I would love if you did. It is a one-time purchase. I know sometimes people don't want to sign up for a recurring payment. I'm just using Patreon as the payment processor and deliverer. It will also be available if you're a patron at the $20 level or above. Of course, it wouldn't make sense not to give it to you. So that's up to you exactly how you want to handle that. So now we know the all-up weight. The next thing we need to do to calculate the disk loading is get the prop size. And what we're going to do is we're going to work backwards. If we know the target disk loading and the all-up weight, then we can work backwards to produce a certain prop diameter that matches those parameters. The formula is right here. And so, for example, if we say a 2 kilogram payload with a target disk loading of 22, we crunch the numbers and it tells us that we will get a prop of 7.9 inches. So we need basically an 8-inch prop to give us a disk loading of just about 22. If we were to go lower, that disk loading would go up. If we were to go higher, that disk loading would go down. And that gives us a ballpark for what size prop we should be shooting for. If you go back to the spreadsheet does it in a slightly different order. In the spreadsheet, we just put in the target prop diameter and it tells us the disk loading. We just basically trial and error. 6 gives us that's too high. 7-inch, that's still too high. 8-inch gives us a disk loading of 22. Hypothetically, 9-inch would be 17, and I can just find a prop size because you know like what size props are. If it tells you you get an 8.6-inch prop, that doesn't help you very much. So you can just put in actual prop sizes to get the disk loading that you're shooting for. So let's recap what we know at this point. We have an estimated all-up weight, we have an estimated battery weight, of course we know the payload weight, and we know the prop size. The next step is going to be to select our battery voltage. And the good news is that there is no math here. I really wanted to give you a formula, but I couldn't come up with one, and we just use a table. This table shows the recommended battery voltage for a given prop diameter. And in case you're thinking, well, is it that simple? Just the bigger the prop, the higher the battery voltage. Yeah, it basically is. There's a little bit of wiggle room in there, but basically below a certain prop size, there's not really an advantage to going to a higher battery voltage, and eventually you end up having to have such low kV motors that everything just falls apart. And then above a certain prop size, it really doesn't make sense to be below a certain voltage. So what we do is we just look at what works in the real world, we make a table, and here it is. Now, I'm guessing that many people flying a payload aren't going to be using a 31 millimeter prop or a 40 millimeter prop, but they're on the table just in case, because why not? And of course, there's some wiggliness in this table, like for 31 millimeter, that's 65 millimeter, whoops, 1S is basically all you use, more or less. But then when you get up to 2-inch and 2.5 inch, it can be anywhere from 2S to 4S. For 3-inch and 3.5 inch, it can be 3S to 4S, but sometimes 6S if you want like a lot of speed, or if you're trying to do like a Cinewhoop, which is relatively high disk loading. And so the general theme here is that the heavier you are, the higher your disk loading, the more likely that you're going to benefit from going to a higher voltage. Whereas if you are lower in the disk loading, you're more likely to get away with using a lower voltage, although you may still get more performance. Like obviously racing drones are very light and have a very low disk loading, but still use relatively high voltage because they just want all the get up and go. Especially here in the 8 to 10 inch category, you'll see a lot of people running 6S in the 8 to 10 inch sizes. And the main reason is that 8S batteries are just that little bit more cumbersome. A lot of chargers don't do 8S, they only go up to 6S. 8S batteries, there's not as much selection in 8S batteries, where there's just a plethora of 6S batteries. So a lot of people will use 6S batteries even after they theoretically could benefit from 8S batteries, and you could even go up as high as 12S at the higher end of the 8 to 10 inch, well, more like the 10 inch, you could be as high as 12S and see some benefit. And then for 13 inches and up, we just say 12S. And obviously, if you know the real world, you know that as props get even bigger and bigger and bigger, you might be doing 14S, you might even be doing a higher voltage. You don't see a lot of people going over about 12 or 14S, because once you get above about 50 volts, the systems get a little bit more complicated in terms of safety and in terms of the electronics. But suffice it to say, you know, that last line that says 13 inches and up, 12S is not like the end-all be-all of battery voltages, but it just sort of like that's where the table's going to stop. Next, we select the size of the motor. And again, I tried to come up with a formula, and there's too many variables to really pin it down. In fact, this is one of the sections where there is the most additional information about, like, okay, here's the table. Just pick one, right? But what's the difference between like a wide and flat motor versus a narrow and tall motor? Does that affect torque? Does that affect responsiveness? Does that affect linearity? Those are not things that we're going to go into in this video. It's because this is just about picking stuff, but it's all here in this document. What the effect of a wider, flatter motor versus a narrower, taller motor is. Debunking the myth that wider motors make more torque. Why don't wider motors make more torque? Actually, there's a reason. It has to do with the size of the magnets of the narrower, flatter, of the wider, flatter motor. It's all in the document, and basically, if you want that stuff, you can go ahead. Well, you can just, I guess you could just pause the video and read it yourself off the screen, or you could go ahead to the link in the video description below and get the document. But basically what we're going to do is we're going to look at this table, and for our given prop size, we're going to have an approximate motor dimensions that we're going to shoot for. These are not the only dimensions that you could possibly use. You'll see people sometimes using 30 millimeter motors for 7-inch and 8-inch props. We only list 2806, 2808, and 2809. You can go a little bit outside this. This is just a starting point, but it's a pretty good starting point, and it pretty much reflects the standard motor sizes that are most often used in the real world for these given prop sizes. As you see here in the 5-inch category, we've got standard sizes of 2306 and 2207, which are more or less the same motor volume, not quite. And then 2407, which is nominally a 6-inch motor, but is often used on 5 inches when the 5-inch will be carrying an extra heavy load. Again, go back to the disc loading, and if you're up near the top of the disc loading range in the sort of 18 and higher, let's say, you might want to opt for a slightly larger motor. It's going to have just that little bit more torque, and it's going to have just that little bit more cooling generally, especially if it is a wider motor. It's going to do better with cooling compared to a taller motor. Now that we've selected the motor size, we need to select the motor KV. And KV is basically how fast the motor will want to spin when you apply a voltage across it. The reality is that you're going to look at the motors available in that size class. And the manufacturers of those motors are going to know that they are designed for use with a prop of a certain diameter, and they are probably going to target certain kV values that make sense for that prop. But where do those numbers come from? And the answer is that they come from the maximum prop RPM. So props are most efficient when the tip of the prop is moving at about 60% of the speed of sound. Keep in mind that the prop's efficiency is not the same as the overall system efficiency. So you may have an efficient prop at 60% RPM, but maybe the motor will be more efficient at some other throttle position, and the ESC will be most efficient at some other throttle position. That's not something we're going to dive into. But in general, when selecting a prop, we're going to try to make the prop go, well, not at 60% of the speed of sound, because like maybe we're not going for maximum efficiency. Maybe we want the ability to generate more thrust, but we want to know what the maximum prop RPM is, because when the tip of the prop approaches about 80 to 90% of the speed of sound, very bad things happen. The prop starts to approach, you get these mock effects as it, turbulence and so forth, shock waves, I don't know. The same thing that happens when an airplane breaks the sound barrier, and that was really hard to do until Chuck Yeager did it, and it was a big deal. Well, your prop doesn't want to approach the speed of sound. And so that is a hard limit on how fast the prop can spin. You cannot go faster than that, or very, very bad things will happen. So we want to calculate this number, not necessarily because we're going to use it directly, although we actually will use it directly, but just so we know what the ceiling is on our prop RPM. And here is an example of that formula. Again, we are using inches per minute because we're going for rotations per minute. So minutes is our time unit, and the prop is specified in inches. And so we're using inches per minute here. And then that's the speed of sound in inches per minute divided by pi times d, which is the circumference of the prop's arc. And here's an example of the math. A 5-inch prop as is a max tip speed of 51,589 RPM. So then we will use that number to calculate an approximate motor KV, and we're not going to actually try to hit that number, because if the motor were to actually hit that number again, we would get these mock effects and very, very bad things would happen. Instead, what I did was I looked at the actual KV used by real motors for a given prop size. And of course, there's a lot of variation, especially as you get to very small or very large props. But since we're just trying to start from nothing and put some bounds on our engineering, I decided that approximately 80% of the max RPM is what the KV works out to in the real world, at least for efficient cruising flight. Not necessarily like radical high throttle racing stuff. So what we're going to do is we're going to take the maximum RPM, which again was 51,589 RPM for a 5-inch prop, and we're going to divide that by the cell count times 4.2. And the reason for that is that the RPM equals KV times voltage. So if we don't know the battery voltage, we can't know what the RPM is going to be. So then RPM divided by battery voltage equals KV, and then we multiply by 0.8 to get 80% of that. And this tells us that a 5-inch prop with a 6S battery, so 51,589 RPM, divided by 6 cells times 4.2 volts per cell, we're using the full charge voltage because that's the fastest the prop will ever spin. That gives us 2047 kV. And you can see that that 100% number is about right for what we use for high-speed racing drones. 2,000 to 2,100 kV on 6S is roughly what they tend to cap out at. And they don't break the speed of sound. You see, a real motor will never actually achieve the RPM that the KV says it would, because in reality, there's friction and other losses. And so if you want like the really fastest, most powerful, not very efficient design, then you can actually pick a kV number that would give you the 100% max RPM, and then real world losses will keep you below that 80-90% threshold, probably. But we're going to take 80% of that number, and that gives us 1600 kV. And you can see that, again, that is roughly the range of real kV that is used for a 5-inch prop. Roughly about, say, 1700 to 2100 kV, depending on if I'm going for slow efficiency or top speed. And will those numbers work out as neatly if you do them for a 13-inch prop or a 3-inch prop? Maybe, maybe not, but it gives you a sort of a ballpark to play in. What if we go back to this motor size table and I go looking for motors, and like especially in the 13 to 15 inch category, I go find a 4218 motor, and the kV of that motor is way outside what I calculated as the target range. Probably that motor is intended for use with a different battery voltage. A motor that's designed to produce a certain RPM at 6S is going to be at a different kV than a motor that's designed to produce that same RPM at 12S. They're going to have double or half the kV. And that's another use for this calculation. When you go look at motors, you're going to want the RPM of the motor to roughly fall within the 80 to 100% RPM range that you calculated, as just a reassurance that you're buying a motor designed for the correct battery voltage. That's less of an issue down in the 5-inch and 7-inch category, where 6S is pretty much the standard voltage, and pretty much all motors are made for that voltage. As you get down into the 3-inch and 2-inch category, there's more variation between, say, 3S and 4S, and again, you're going to want to just double check that the motor kV seems correct for the voltage that you're using. It's producing an RPM roughly in that range. Of course, I've also got a table for you that reflects the real world. This is a survey of real world kV that's used on real builds with real motors. It is not all encompassing, but it is a good place to start. And you can also cross-check what you're seeing here if you just want like a top of the head. What kV should I use for a 10-inch drone on 6S? Roughly 900 kV. What kV should I use for a 15-inch on 12S? Roughly 250 kV. Again, just a reference here to kind of help you sanity check what you're seeing as you're selecting motors. Now, we've talked about selecting the prop size, but there is another specification for props that we haven't discussed, and that is the pitch of the prop. The pitch of the prop is how steep the prop blades are, and it definitely affects the performance of the prop. The short version is that low pitch props are better for slow cruising and efficient flight, but have a low top speed. High pitch props are better for times when you will be going very fast, and they will be much less efficient at low speed, but much more effective at high speed. This is discussed more in this section of the report, which talks about the effective pitch on the prop and how it relates to maximum speed. In general, you're probably going to want to stick with lower pitch props because they're going to be more responsive as long as they're making enough thrust for what you need to do. By the way, the pitch of the prop also affects the thrust. In general, higher pitch props will make more thrust but draw more amps. This is the kind of thing that I cannot give you, and I tried, but I couldn't come up with something that I felt good putting out there, and so I cannot give you like a guideline on how pitch affects thrust and efficiency and maximum speed. Basically, what you have to do is, once you've settled on the prop diameter, you just have to go buy different props. You eventually have to build a drone, and you have to like just try it out and see how it performs. I don't know any other way to do it. So you've got a target motor size and a rough range of kV that you're looking for. The next thing you're going to do is you're going to go out there to your favorite FPV store, and you're going to look at what real motors are available to you, because that exact size or that exact kV may not be available. And ultimately, you have to just buy something, right? So let's do an example, and let's not do 5-inch. 5-inch is boring. We'll do 10-inch. 10-inch, so 2810, 2814, 3110, 3115, 3214. That's the rough 28 to 32 millimeters is roughly the sizes I'm looking for. So now I'm going to go over to an FPV store, and 30X, so we'll do 28 and 30XX and larger. So we'll start with 28XX. Here's a 2807. And I'm pretty sure that is more like a 7-inch motor, 2806. So that's not quite big enough for 10-inch according to these guidelines. 2807, 2810. Okay, there we go. There's a 2810. Let's see, 2807, 2808, 2810. Let's see, 2809. That's still a 7-inch motor. I'm pretty sure they put that on the Chimera. 2809, yeah. That's right on the border. I mean, if 2809 is a 7-inch and a 2810 is a 10-inch, that's only a 1 millimeter difference. But like, I don't know, we got to draw the line somewhere. 2810. All right, so we've got some 2810 motors, and then let's also go and look at the 31s. Motors and props, motor size 30XX and larger. Let's see, 3115. Yes, 3115. That would be for if my 10-inch was maybe going to be a little heavier. Here's a 3115, 3115, and lots of 3115s. Here's a 3120. That is not on this list. We'll check. A lot of times if a motor is a weird size and you're not sure if it's going to work for your prop, check the KV. If the KV is just wildly wrong, then it's probably designed for a different prop. Here's a 3120. And for a 10-inch, we are shooting for a 10-inch on 6S. We are shooting for a KV around 900 KV. So we'll go back here and we'll look. This 2810 1500 KV, that's not going to work for us. That's going to be way too high of a KV for a 10-inch prop. That's designed for a different prop. And that's kind of how we use these numbers. That's probably designed for a 7-inch or an 8-inch prop, I would think. So, no good, you're out. 1250 KV, nope, no good, you're out. 1350 KV, all these 28 millimeter ones are going to be too high of a KV. This one's close. Oh, that's a 31 millimeter. So this is 1050 KV. It's a little higher than 900 KV, but I bet, I'm not going to do the math, but I bet if we did the 80% to 100%, that would be right in that range. So that's a suitable motor for this prop. Here is my choice of 900 KV or lower KVs. Those lower KVs are for if you're using a higher battery voltage. So just 6/8. That's 0.75. So if I were to use an 8S battery instead of a 6S battery, I would take 0.75 times 900 kV, and I would be shooting for about 675 kV. That's conveniently right about here. So that 900 kV is right for a 10-inch prop on 6S battery. 640 kV is about right for a 10-inch prop on an 8S battery. It will produce about the same RPM. Do you follow that math? Yeah, super easy, right? Unfortunately, the 640 kV is not available, so F me. What else have we got? 900 or 1050 kV, that's perfect. For probably 1050 kV is probably more like for a 9-inch prop, but it would be a little bit more performant on a 10-inch prop at the cost of a little bit more amp draw. 900 kV would be just about perfect for a 10-inch prop, just with a little bit less amp draw. Well, the 900 is out of stock. I would buy the 1050 kV, and if I wanted to, I could do a motor output limit in Betaflight to slow it down, and it would probably perform about the same. Here we go. 400. This one's no good. This is not for us. This is not for our prop, or it's not for our battery voltage. The KV is wildly wrong. That motor is out of the question. Likewise, this one, 3120, 500 kV. Like, if I were doing 10-inch on 12S, 500 kV would be about right. 6S times 900 kV equals a certain RPM. So then what S at 500 kV? It's roughly half. That's not exactly half, but you roughly double the voltage, you roughly have the kV, and you produce the same RPM at the output. So, but that's for something else. 3120 at 700 kV. So that's probably for a larger prop, but it would probably work on 10-inch on 6S. It would probably be just about perfect on 10-inch on 8S, though. Let's, again, 75% 8S. So if I do 700 divided by 0.75, that gives me 933. So 700 kV on 8S is equivalent to 933 kV on 6S, which is just about perfect. This would be a great motor if I was doing 8S 10-inch props. Okay. I wanted to walk you through that because, like, we've got these abstract tables. How do we make that concrete? We've got this abstract KV range. How do we make that concrete? And that's the answer to how you do it. You're going to take the tables and then you're going to go look at real motors and you're going to say, okay, these are my choices. And you're just going to pick one and you're going to buy it. You're going to build a drone and you're going to see if it works. Or at least you're not picking it like, oh, I bought a 3120 motor, which is the right size for 10-inch, but my KV was wildly off. That's what I'm trying to save you from. So now we've got the motor and the prop. The next thing we need to do is select the battery. And we're going to start by selecting the battery chemistry. The chemistry of the battery is going to be dictated by the C rate, and the C rate is dictated by how long the aircraft needs to stay in the air. This insight was given to me by by Matthew Barnard, the owner of Upgrade Energy, who manufactures batteries. And it blew my freaking mind, and I didn't understand it at first, and I think you're going to have the same reaction. What he said was that if you have an aircraft that needs to stay in the air for 1 hour, then the C rate of the battery needs to be about 1 C. How big is the battery? Doesn't matter. The battery is big enough that it can stay in the air for 1 hour. How big is that? I don't know. It doesn't matter. It all cancels out. By definition, if the battery is fully discharged after 1 hour, it discharged at a rate of 1 C. That's the definition of C rate. C rate is whatever discharge rate discharges the battery in 1 hour. So, the way that Matthew Barnard specs batteries, and I'm stealing this from him and I'm giving it to you. Sorry, Matthew. Well, he's probably fine with it. Is you ask, how long does the aircraft need to stay in the air? If it's 1 hour, that's a 1 C battery. If it's a half hour, that's a 2 C battery. If it's 20 minutes, that's a 3 C battery. If it's 15 minutes, that's a 4 C battery. And so on and so on and so on. Basically, the necessary battery C rate is 1 over the time in air in hours. Basically, we're going to take the expected flight time of the battery, and that's going to give us the floor of the C rate. We can't go less than that, right? That's our best case scenario. We're going to add a little bit of C rate in there to cover any peaks in current, and then we're going to choose a battery chemistry based on that C rate. And if the C rate is between about 10 to 12 or higher, we're going to use LiPo pouch cells. Okay. If the C rate is between 5 and 10, we're going to use high C cylinder cells. They call them power cells. Examples are the Molicel P28A, 18650, and the Molicel P54B, 4500, 21700. Those are power cells. They have a higher C rate with a lower energy density. If the C rate is less than 5, we're going to use high milliamp hour cylinder cells. They're also known as energy cells. They're high energy density with a lower C rating. Examples include the Panasonic 50S 21700 and the LG M50LT 21700. And then if the C rate is less than 3 and price is no object, you're going to use Amprius silicone anode cells. Amprius silicone anode cells have like 3 times the flight time, gram for gram, of any other chemistry that you could use, but they're wildly expensive. You can get them from Upgrade Energy. I'm not even sure you can buy Amprius cells without being an Amprius dealer, but Upgrade Energy, their gold packs have Amprius SaO8 or other Amprius silicone anode cells in them, and they have like wildly high energy density, basically triple the flight time, double the flight time, maybe compare it gram for gram, but you have to fit in under that 3C rate. Keep in mind though that 3C rate is relative to a preposterously high amp hours. So this battery is a 22.2 amp hour, so 3C is like 60 amps. And if you compare it gram for gram against a cylinder cell, it might only be rated for 30 amps. So even though it's 3C, it's still putting out a few amps because of its ridiculously high energy density. These batteries are preposterously expensive, and they're a little bit fragile. Like if you mistreat them, they will spectacularly light on fire in a very, very unfriendly way. So like only use them if you absolutely need to double or triple your flight time. Price no object. And for more typical uses, stick to more cheaper and a little bit safer cells. So basically what we need to do is, we don't need to actually calculate a C rate. Is it 9 or 8 or 7? Or what we need to do is we need to decide which of these categories our C rate is going to be in. And you might be able to do that just like from guesswork. If I'm doing a racing drone that's going to be pulling 60, 80, 100 amps, maybe more, obviously pouch cells are, well, these days, cylinder cells are getting better and better, but pouch cells are probably going to be the ones that I'm going to use. Anyway, we're going to settle on a chemistry. And then we need to go buy a real battery, right? But how many milliamp hours should that real battery be? And just like we did with the motors, we're going to do some math to get us in the ballpark, and then we're going to go look at real batteries and try and see how they match up. What we're going to do is we're going to take the energy density of our chemistry. And these are roughly standard numbers. The real world varies some, but this is a good ballpark. The energy density is going to tell us the number of watt hours per kilogram, and then we're going to use that to calculate a capacity of the battery based on the weight of the battery that we calculated back in the first step. So if we know that our battery is going to be 1 kilogram and it's going to be a 6S LiPo, then that LiPo is going to have an energy density between 135 to 175 watt-hours per kilogram. We then do the math and we find that that battery is going to be roughly between 5.45 amp hours and 7.00 amp hours. We are then going to go look for a 6S pack, and we're going to look for a 6S pack that weighs about 1 kilogram, and it should come in at roughly 5.45 to 7.00 amp hours. In the real world, you may find that some of these assumptions don't hold, and you might need to decide between sticking with your weight, which again, the weight was we just swagged it based on 60% of the payload, or sticking with your milliamp hours and then trying to get your C rating and your amps correct. This is a place where you'll have to decide which way you want to go. Keep in mind that if you are not using the full payload capacity, like if you're trying to do a drone, a freestyle drone that doesn't carry a GoPro, so there is no payload, then your disk loading assumes you have 60% of the dry weight in battery and 60% of the dry weight in payload. So if you have a battery but no payload, you could easily go to a little bit heavier battery, right? Or you could go to a lower disk loading by making the all-up weight less. You just sort of figure out which way you want to wiggle that. What I wanted to do in this video is give you the beginning of the process to get you in the ballpark of correct, and I hope that you agree with me that we've accomplished it. If you do, please consider joining my Patreon. It's a great way for you to support the work that I do here, or please consider buying a copy of this spreadsheet, which, as I mentioned, does all of the math for you. You just, let's do one. Your payload weighs 1,500 grams. It means my all-up weight is going to be roughly 3,300 grams. That gives me a disk loading of 16. Go a little higher. What if I went to a 7-inch prop? 21. Disk loading at 21, I don't know. Maybe I want it to be a little more maneuverable, so we're going to go up to an 8-inch prop. Great, disk loading of 16. Maybe I want it to be super maneuverable. I want to sling that camera around. I want to chase a car. Let's go up to a 10-inch prop. Oh, disk loading of 11. That's going to give me roughly 5-inch freestyle drone performance on a 10-inch. Well, obviously not exactly, but there's going to be lots of agility. Great. So then we are going to select the battery voltage. We're doing 10-inch. Let's say we're going to do 8S on 10-inch, right? We want max power, and we're low in the disk loading, so we don't need 8S. And it is going to complicate our KV selection. Okay, we'll use 6S. We'll keep it simple. Especially when the disk loading is low, we can afford to use a lower voltage battery. So we'll use 6S. Great, 6S. Motor size. We're going to pick one of those motors that we saw, 3110 900 kV, like the Brother Hobby 3110 900 kV would be a good choice. Motor kV, 900 kV. And then for battery chemistry, let's say we need the aircraft to fly for 15 minutes, right? We're going to go chase a car around a track. C rate of 4. What if it's 10 minutes? C rate of 6. It looks like we are potentially... We could use some of these cells, especially the newer tabless cells. We could probably get away with using them, but maybe it would be better with LiPo cells. We definitely wouldn't want to use the energy cells or the Amprius silicon anode cells. And then as far as battery capacity goes, we're going to choose 135 times 3.7. We're going to be shooting for roughly a 4.4 amp hours to 75 or to 6 amp hour battery. So I'm going to search for the Upgrade Energy Red, which I know for a fact are power cells, usually 21700s. I'm looking for roughly 4 to 6 amp hours. Here's a 5 amp hour 4S1PO. That's no good. I need a 6S. 6S2P 10 amp hours. 6S1P 5 amp hours. 6S1P 5 amp hours. Yes. So let's look at this battery. First of all, how does the weight fit in with our expectations? 0.4 kg. We said that the battery would be roughly 900 grams. It's 400 grams. So we are way higher in the density than this assumption would be. Okay. So I could either use that battery and have a lower disk loading, or I could double up that battery in parallel and have a higher disk loading, have the same disk loading by spending more weight on the battery. Let's just double check the motor. Brother Hobby 3110 900 kV. We'll go ahead and we will just take a look at this motor and see if we can find an amp rating for this motor. Test data, perfect. 900 kV, 9 by, so they've got 900 kV for the 9-inch prop and 730 kV for the 10-inch prop. If you say so, it is pulling 37 amps at 25 volts. Yeah, so it's pulling 37 amps max on the test stand with a 10-inch prop at 730 kV. What if I were to go with a higher kV? Let's see, the 11-inch prop on 730 kV, 38 amps, and the 900 kV on a 9-inch prop, 47 amps. Okay, so it sounds like I probably don't want to do the 900 kV on a 10-inch prop, except I have in real life, so I know it's okay. But based on these test results, let's see, what's my thrust? My thrust is 3203, so I'm getting 3 kilograms of thrust per motor on the 9-inch prop at 900 kV. My estimated all-up weight is 3,300. So basically, I'm getting a thrust-to-weight ratio of 4:1. That's not spectacular. That's not spectacular. I need the battery to be a little lighter, or the aircraft to be a little lighter, or I need more thrust. How about my 11-inch prop? 11 by 7 by 3 is going to give me 38 amps at, again, it's about the same, 3347. It's just more efficient. So what I'm going to do is I'm going to do the 900 kV on 10-inch. That's going to give me just a little bit more thrust and more amps. So maybe I'm going to pull 50 or 60 amps. And you might think 50 or 60 amps times 4 motors is 240 amps. But bear in mind, again, this is on a test stand, which is always going to inflate the number because the prop doesn't unload because the test stand never starts moving through the air. And it's at 100% throttle, so you might get transients that are a little bit high. But like realistically, you might see half that number and it's under sustained load. So let's say 100 amps, 90 to 100 amps. What's this rated for? Oh, here it is. 50 amp burst and high energy density package. So 50 amps. So if I were to get a 2P version, a 6S 2P version of this, 6S 4P, no, 6S 3P, 15 amp hours. What's that weigh? It's going to be too much. I need a 6S 2P 10 amp hour. There we go. 6S 2P 10 amp hour rated for 100 amps. This, and it's going to weigh about 900 grams, isn't it? Yeah, 860 grams. Boom. That's the perfect battery for this build. Or we could go with the 6S 3P, and that is going to be rated for 150 amps, and it is going to weigh 1.4 kilograms, which, again, we're assuming a 10-inch prop, 1.4 kilograms. So I'm just going to change this to 1400, and then that's going to give me a disk loading of 12, which, again, is just fine. I could go with the bigger battery if I want a little bit more flight time and a little bit more safety on the amp draw for the motors, or I could go with the slightly smaller battery and be just a little bit more on the edge and get a slightly more agile craft. That's how we do it. Put your questions down in the comments, or if you want to DM me, you can DM me and I'll try and help you sort through these kind of problems. That's what I do. I hope you have enjoyed this, and I will see you in the next one, but ooh, it won't be this cool. Oh, this is good shit. I'm really happy with this video. I hope you are too.